Hello, and welcome to lesson number 4 of Mathematics for IT. This lesson is on set operations and identities. Let's first look at the learning outcomes. So by the end of this lesson, you should be able to apply set operations over given sets and apply basic theorems in set theory for problem solving and apply the duality principle for the sets and use Venn diagrammatic representation of sets for real-world applications. So we will start by looking at the first set operation, which is union. So let's try to understand what is meant by set union. So union of two sets A and B, denoted by A union B, is the set of all elements which belongs to A or to B. So in the below Venn diagram, you see the two sets A and B, and you can see that these two sets are not disjoint, which means they have some elements in common. And you can see the colored area in green represent the union of sets A and B. And the next important operation is intersection. So the intersection of two sets A and B, they are denoted by A intersection B. It's an inverted U symbol. That is the elements which belongs to both A and B. In other words, which are common to both A and B. So once again, you have a mathematical notation as well as Venn diagrammatic notation, and you can see the colored area in green, which is common to both sets A and B, is denoted by, and it does represent the intersection of A and B. So let's now look at some simple examples to understand the union and intersection. So you have sets A, which includes 1, 2, 3, 4, set B, which includes 3, 4, 5, 6, 7, and set C, which includes 2, 3, 8, 9. And for A union B, you have all elements of A and B, which is the numbers from 1 to 7. And when you take set A union set C, you have all the elements that belong to sets A and C. Similarly, for B union C, you have all the elements in B and C. And then you can have A intersection B, which includes 3 and 4, which are the common symbols or common elements of sets A and B. Similarly, for set A intersection set C, you have 2 and 3, and B intersection C, you have only just one element, which is number 3. So I think these examples are quite straightforward. And now the next operation, which is the complement. So the complement of set A, for example, is denoted by A superscript C, which denotes complement. So this is the set of elements which belong to U, that means the universal set, but do not belong to A. So you have the mathematical representation as well as the Venn diagram. You have the colored in green part. They are the elements, or that is the area which is not represented by A. So except A, everything else. So this is the complement of A. And then the set difference. So difference of sets A and B, denoted by A backslash B, is the set of elements which belong to A but do not belong to B, only belonging to A, no other set. So in the Venn diagram, you can see the colored area in green denotes the difference between sets A and B, which in other words, it contains the elements only included in A. but not any other sets, not in B or not in the any other set. And then the concept of symmetric difference. So let's look at what is meant by that. The symmetric difference of sets A and B, denoted by this special plus sign within a circle, consists of those elements which belong to A or B, but not to both. So in the Venn diagram, you can see you have two sets A and B, which are not disjoint, and they have things in common or elements in common, but the symmetric difference refers to anything that is not common to A and B. Okay, so that's denoted in the Venn diagram given in figure 4.5. Okay, now let's go for an example. Suppose the universal set is the natural numbers. So we take two sets, or actually four sets. A is 1, 2, 3, 4. B is 3, 4, 5, 6, 7. C is 2, 3, 8, 9. And E is 2, 4, 6, which are the even numbers. So you can see that E is an infinite set. All the other A, B, and C are finite sets. So here E denotes the set of even integers. Then let's look at what is the complement of A, because we have defined the set A, which has finite amount of elements, which are 4 elements. But once you take the complement of A, everything except the elements of A within the universal set. So what is obtained from that is numbers 5, 6, 7, all the natural numbers that do not include in A. So that is the complement of A. Similarly, the complement of B, everything other than the element of B, which are included in the universal set, which is the set of real the natural numbers. And similarly, for the complement of E, so you can see that E is the set of even or all the even numbers, and complement of E is all the odd numbers in this case. So that is complement of E is the set of odd positive integers in this case. So you can also calculate, or you can also derive the set differences. Difference of A and B is 1 and 2, A and C is 1 and 4, B and C is 4, 5, 6, 7, and so on. And you can also infer the values for other differences that are given in the example. So furthermore, you can also find out the symmetric differences of sets A and B, B and C, A and C, and so on. So I think this example should give you an idea of the concepts of the union, intersection, the complement, as well as the difference, and also the symmetric difference of sets. Now, with that, we take a step forward and look at some general laws of algebra that are related to sets and their operations. So we begin with, we have the idempotent law, which is A union A is equal to A, and also A intersection A is also equal to A. And then you can also identify the laws, the associative law, commutative law, distributive law, identity law, involution law, complement law, and De Morgan's law. So all these laws that refer to algebra in relation to set operations will be helpful in the calculations or in the operations that you will be seeing or that you will be dealing with in the future lessons. Now let's look at another important concept in set theory, which is duality. So suppose E is an equation in set algebra, and let's look at what is meant by the dual of E. So we can take the equation E and do a transformation by replacing each occurrence of the union symbol, intersection symbol, the universal set, and the empty set in E by the counterparts, which are the intersection symbol, union symbol, the null set, and the universal set, respectively. So by doing that transformation, you obtain what we call the dual of the equation E. So here you have an example. So the statement here is U intersection A, U is the universal set here, U intersection A, union B intersection A is equal to A. So this is the original statement, algebraic statement. And how do you obtain the dual? You replace the universal set by the null set, union symbol by the intersection symbol with the union symbol, and if you have null set, you replace that by the universal set symbol. So in this case, you don't have the null set, but if you had one, you need to replace that by the universal set symbol. Right, so that is the concept of duality. Now, next step is counting elements in finite sets. You understand, you already know what is meant by finite sets, which means it has a finite number of elements. So we have a lemma here. Suppose A and B are finite and disjoint sets. Disjoint, if you can recall, those are sets which have no elements in common. And for this kind of two sets, the union of A and B is finite and is given by the number of elements of the union of A and B is equal to the number of elements of A plus the number of elements in B. So I think this is a straightforward representation. So you can refer to the proof as well. So in counting the elements of A union B, first count those that are in A. Then there are NA number of elements in A. So that's the representation. The only other elements of A union B are those that are B but are not in A. But we know that these two sets are disjoint since because of that reason, we don't have common elements. In other words, the intersection of A and B does not have any elements. So there are NB elements in B. Therefore, eventually you have the number of the elements of A union B is equal to the number of elements in A plus the number of elements in B, because these two sets are disjoint finite sets. So moving on, for any sets A and B, the set A is the disjoint union of A difference B. That is the difference of A and B and A intersection B. So this leads to a corollary. So what is given in this corollary is, let A and B finite sets, then the number of elements in the difference of A and B is equal to number of elements of A minus the number of elements of the intersection between A and B. So I think this is also straightforward to understand, because you leave out whatever the common elements, because A and B are not disjoint. and which means that A and B have some elements in common. And then in order to take the difference of A and B, you need to take out whatever the common elements. And then you are left with the elements that are only included in A and not included in B. So this is how you find out the difference of sets. So moving on, we move on to another corollary. So given any set A, recall that the universal set U is the disjoint union of A and A. Okay, accordingly, from lemma 4.1, we can prove that this corollary is true. Okay, so let A be a subset of finite universal set U. Then the number of elements in the complement of A should be equal to the number of elements in the universal set minus the number of elements in A. Because in the complement, what we are looking at is all the elements except that are included in A. Okay, that's why we subtract the elements that are included in A from the number of elements in the universal set. So this is corollary 4.2. And we move on to another principle. So there's an expression for the number of elements in the union of A and B, even when they are not disjoint. In other words, even when they have some elements in common. So this principle is called inclusion-exclusion principle. So let's look at what this principle is telling us. So theorem, inclusion-exclusion principle. Suppose A and B are finite sets. Note that these two sets are not disjoint. So then A union B and A intersection B are also finite. Then you can have number of elements in A union B is equal to number of elements of A plus number of elements of B, but you need to subtract the number of elements in the intersection set. All right. So this is the principle denoted by inclusion-exclusion principle. You need to exclude whatever the elements that are in the intersection set of A and B. So that is, define the number of elements in A or B by first adding all the elements of A and B. So that's why we refer that to as inclusion. And then we need to subtract the elements in the intersection set. So this step, we exclude some elements. What do we exclude? We exclude whatever the elements that are in the intersection set of A and B. So because, why do we do that? Otherwise, it will be counted twice, because we already counted them when we included the elements from A and B. But we need to, in order to remove the duplication, we need to subtract whatever the number of elements that were in the intersection set. So we can apply this result to obtain a similar expression for three sets as well. So until now, we had only sets A and B, two sets, but we can extend this to three sets as well. Let's say we have A, B, and C finite sets, and then we can derive a expression for A union B union C, which is equal to number of elements of A plus number of elements of B, number of elements of C, and then you need to subtract all the intersection sets, A intersection B, A intersection C, also B intersection C, plus all the elements that are common to all three sets. So this gives the expression for the number of elements of three finite sets, which may have elements in common. So here we go through a simple example. Suppose list A contains the 30 students in a mathematics class, and list B contains 35 students in an English class. And suppose there are 20 names in both lists. That means for A and B, there are 20 students in common. So you're asked to find out the number of students only on list A, only on list B, on lists A or B, on exactly one list. So let's see how this is done. So we can represent this very simply in a Venn diagram. So in the solution, you can have a Venn diagram as given in figure 4.6. So we have number of elements in A is 30, number of elements in B is 35, and the intersection is also given, which is the common number of students of A and B, which is 20. So how do we calculate part A, which is the number of students only on list A? We need to take out whatever the common students in A and B from the number of students in the set A. Okay, so we have NA minus NA intersection B, which is 30 minus 20, which is equal to 10. And similarly, for the number of students only on list B, we can adhere to a similar procedure, which gives you 35 minus 20, which is equal to 50. And then for part C, we use the inclusion-exclusion principle to get the number of students that are either in the mathematics class or the English class. So how do we do that? We have the number of elements of the union set is equal to NA plus NB minus NA intersection B. So we get 30 plus 35 minus 20, which is equal to 45. Therefore, the number of students on list A or B is equal to 45. So that is calculated using the inclusion-exclusion principle. And for part D, by using A and B, 10 plus 15, which is equal to 25. Therefore, the number of students on exactly one list is 25. So this is the methods. These are the procedures that we use to do these kind of calculations, which are related to sets and their operations. So with that, we reach the end of the lesson. And so this lesson was about set operations and identities. So in the next lesson, we will be covering the propositional logic. Thank you.